Hello everyone, Dr. Hasbullah here, and I hope that everybody is doing well. And in this video, we are going to be looking at buoyancy and stability. I think when we talk about buoyancy, then we cannot escape the fact that buoyancy law is Archimedes' principle. And Archimedes' principle says that the buoyant force is equal to the weight of the displaced fluid. Okay, so Archimedes' principle states that the buoyant force is equal to the weight of the displaced fluid. And we know that weight equal to mg, and that m, the mass, is actually rho times volume times gravity. So this becomes the specific weight times volume. And one very important thing that you must remember is that this is the volume of the displaced fluid. Okay, sometimes we tend to get confused between the volume of the object or the volume of the displaced fluid. But if you are to calculate the buoyant force, remember that this must be the volume of the displaced fluid and not the volume of the object. So if the object is floating, then the volume of the object and the volume of displaced fluid is going to be different. Correct? But if the object is submerged under the water, then the volume of the displaced fluid will be equal to the volume of the object. Now, let me give you an example. Let's say an object weighs at 890 Newton. But when this object is submerged underwater, the weight is now 667 Newton. Now the question is, what is the specific weight and what is the specific gravity of that particular object? Okay, so now let's see how we can solve this, right? And if I draw the free body diagram of that particular object, we know that this object has weight. Okay, and this weight is 890 Newton. Now, when this object is submerged underwater, you also have the buoyancy force that is acting on that object. And we also have a rope here that is under tension and is holding the object. And the force that is on that rope is 667 Newton. Okay, so if I do the summation of force in x direction, I'm going to get 667 plus the buoyant force equal to weight of the object. And we know that the weight of the object is 890 Newton. So my buoyant force would be 890 minus 667. And that equates to 90 minus 667. That is 223 Newton. Now, if I go back to my original equation for Archimedes' principle, then I know that my FB is gamma times volume. So I'm going to write it again here. So this is actually gamma times volume equal to 223 Newton. Now, we know that gamma should be gamma for water because this is buoyant force. The gamma should be gamma for water and the volume should be volume of water. But in this case, because the object is fully submerged, then the volume of displaced water is equal to the volume of the object. And gamma of water is simply 9810. So this is the volume of the object equal to 223. And that gives you the volume of that object is 223 divided 9810 equal to 0.0227 meter cube. Now, what is it that we were looking for? We were looking for gamma of the object and SG for the object. Okay, so gamma for the object, I'm going to label it gamma O, must equal to rho of the object times G. And rho is simply mass divided by volume times G. And mass times G is weight divided by volume. We know the weight of the object, that is the weight of the object in the air, 890 Newton, divided by the volume of the object, which is 0.0227. And this is equal to, divided by answer, so this is 39,152, and the unit for gamma is Newton per meter cube. Right, so that solves one question. And the other question is to find the specific gravity. So specific gravity of the object is equal to density of object divided by density of water. And because gravity is similar, doesn't matter if it's for object or for water. So you can also say that this is gamma of object divided by gamma of water. And this is equal to 39152 divided by 9810. And you end up with 3.99. And as usual, specific gravity does not have units. Okay, and that's all you need to know basically about buoyancy. Of course, there are other complicated problems that are related with buoyancy, but as long as you know Archimedes' principle, which says that the buoyant force is equal to the weight of the displaced fluid, then you should be fine. So right now, we are going to move on to a particular topic that I think is new to you, which is called stability. Now, how does stability relates with buoyancy? Now, if the object looks like, for example, my calculator, and this is a water line. Let's say the object floats on water, okay? And if it floats like this, then there's no problem. The object is stable. But if it floats like this, then if there is any rotation that is applied to the object, let's say it rotates this way, okay, how do you know whether the object will go back to its original position or is it going to be unstable and topple? Now, of course, that's a simple example, but look at ships. Why do you think ship stays upright even though there are heavy waves? Because ships rolls all the time. Yet, every time it rolls, it goes back to its original position. And that is stability. And engineers have calculated precisely how much roll that the ships can take before it topples over. Now, before we go to the floating object, now let's take a look at the object that is submerged underwater. Okay, so first, for submerged cases, and let's say the object looks like this, where you have the buoyancy force that acts on the centroid of the object, and I'm going to call this C. And also that object has a center of gravity that is exactly the same as center of buoyancy. So let's say this is the G. Okay, and this is the weight of the object. If this is the case, then this is called neutral. But it is not necessary that G and C is at the same place. It could also look something like this. Okay, let's say that C is at the bottom and G is on top. So this is your weight and this is your buoyant force. So this is your center of buoyancy and this is the center of gravity. Okay, in this position, it looks stable, correct? But what happens if there is a slight rotation? Okay, let's say this is going to rotate counterclockwise. Okay, so what happens to the G and C? C is going to be here and buoyant force goes upward and G is going to be here where the weight is going downward. Now, do you see what just happens? These forces is going to create a moment that will topple the object. Okay, so in this case, where G is on top of C, then the object is unstable. There is one more case, whereas G is below C. And let's see what that looks like. Okay, so now let's say this is G, and this is the weight, and this is C. This is your buoyant force. Now C is on top of G. Now let's take a look if a little rotation is applied to the object. What happens to the stability? So now, this acts downward, this is your G, and this acts upward, this is your C. This is your buoyant force and this is your weight. Now, what happens is that it has the moment that looks something like this, okay? So, when you rotate the object counterclockwise, there is a moment that's developed which is going to turn the object clockwise. So, what happens is that the object remains stable. In this case, you call it stable. Okay, and that is the case for submerged object. This is quite straightforward. If G is on top of C, the object is unstable. If G is below C, the object is stable. But second case is for floating object. Now floating object is a little bit more complicated than that. Okay, now let's take a look at why does this happen. Why is it a little bit complicated than the submerged body? Let's say that you have a ship. Okay, that looks something like that, and this is the water line. Okay, and C is the center of buoyancy, so C is located here. This is your buoyant force, and G is the center of gravity, which is the weight of the ship. And let's say that G is here. Okay, and the force of the weight is going down. For submerged body just now, if you have C that is under G, then immediately you know that the object is not stable. Okay, but that is submerged body. Luckily, this doesn't happen on floating bodies, right? So floating object, even though when C is under G, there are certain rules that can ensure that this object is still stable. For floating object, there is an imaginary point that is called M, and the distance between M and G is called the metacentric height. Or maybe we're going to write this as GM. So in order for the floating object to remain stable, GM value must be positive. So even though G is on top of C, as long as the metacentric height is positive, the distance between G and M is positive, the object will still be stable. But if GM is negative, then the object is unstable. Now, what it means physically when GM is positive is that M is on top of G. If M is below G, then it becomes a GM negative, which means that the body will be unstable. So let's see an example of what happens to the ship if GM is positive. Okay, when GM is positive, when you rotate the ship a little bit, so the ship becomes like this, and G is still here, and there's a force going downward. This is G. But if M is positive, which means M is on top of G, then the center of buoyancy will be here. Let's call this C1. Okay, so what happens is that this is the center of buoyancy, FB, and therefore M is on top of C1. Okay, so what happens is that this becomes the restoring moment that rotates the ship back again into position, into a stable position. And this is the water line. And this is why ships is very stable. Very rarely that you see ships topple over because GM is always positive. Okay, and how do we calculate GM? We're going to calculate GM using this formula. GM equal to IO over volume minus CG. I think by now you already know what I is. I is the second moment of area. This is volume, and this is the distance between C and G. Okay, remember C is the center of buoyancy, which means that C is the center of the displaced fluid, and G is the centroid of the object, or the center of gravity of the object. And in order to show you how to use this equation, let's work on an example. Okay, let's say you have a cylinder, and this cylinder floats on water. And this is your water line. The diameter of this cylinder is 0.25. And the length of this cylinder is also 0.25. And also the specific weight of the cylinder is given as 8,000 Newton per meter cube. Now the question for you is very simple. Will the object float upright? Okay, so will the object float upright? So basically, the question wants to know whether the object is stable or not. And to find that, it's not that difficult. We just need to find the GM. If GM is positive, then yes, the object will stay upright, the object will be stable. But if GM is negative, then the object will topple over. So it means that the object is not stable. Now let's take a look at our equation. So GM is IO over volume minus CG. So GM is equal to IO over volume minus CG. So let's find IO first. And IO is the second moment of area for a circle because the cylinder here has a circular cross-section and it stays upright. If the object, let's say, has a rectangular cross-section, then I would be BH cubed over 12. But now it's circular. This is the first time that we see it. So let's see it in the table. What is the second moment of area for circle? Right? And the second moment of area for circle is pi d to the power of 4 divided by 64. Now let's get back to our note. So IO is pi d to the power of 4 divided by 64. This is simply pi. D is 0.25 to the power of 4 divided by 64. And IO is pi times 0.25 to the power of 4 divided by 64. That is 1.917 times 10 to the power of minus 4. And the unit is meter to the power of 4. Okay, next we need to find volume. And I think I forgot to mention before that this volume is the volume for displaced fluid. Okay, be very careful. This is not the volume of the object, but this is the volume of the displaced fluid. Okay, now let's take a look at what is our volume of the water. And to find volume, we know that gamma is equal to rho G and rho is equal to M over V times G. So V is mg over gamma, and this is simply W over gamma. Okay, and because we are looking for the displaced volume, alright, so this is V displaced. W must also W of the displaced water. But because the object is floating, it means that the buoyancy force is equal to the weight of the object. That's why it is floating. And buoyancy force is equal to the weight of the displaced fluid. This means that the weight of the displaced water is the weight of the object. And I think that information is given when it states here that gamma for the object is 8,000 Newton per meter cube. But before that, looking back at this equation, we are looking for the volume of the displaced water, meaning that that must be the weight of the displaced water divided by gamma of displaced water. Okay, because there are so many gammas now. There are two gammas, gammas of the object and gammas of water. So you need to be careful. Okay, so here gamma of displaced water is 9810 and weight of the displaced water, I'm going to label it WD, is equal to M times G. And mass is actually density times volume times gravity. So in here you have the gamma of object times the volume of object. And gamma of object is again 8,000 Newton per meter cube. This is 8,000 times the volume of the object. So this is pi times the diameter square over 4. Diameter is 0.25 square over 4 times the length is 0.25. So now we will have our volume of displaced water. Now let's try to get this. So this is pi times 0.25 square divided by 4 times 0.25 times 8,000 divided by 0.0. That is 0.01 meter cube. Okay, now that we have I and we already have V, so what is CG now? CG is the distance between the center of buoyancy force and the center of gravity of the object. So if the displaced water is here, so C should be somewhere here. So this is your C, and I'm just going to draw, let's say the border for the object is here. So the centroid of the object, G, must be somewhere along here. So this is your G. And we know that G is simply 0.25 divided by 2. So this is 0.125 meter. But what is the distance here? Because we are looking for this. This is the CG. In order to find CG, we need to find the length of the object that is submerged underwater. And I think that's quite obvious how to find this, because now we already know the volume of the displaced water and we know the shape of the object. Okay, so volume of the displaced water just now, I'm going to call this L. Okay, so volume of the displaced water, this is 0.01, must equal to pi d square over 4 times L. Right? So L is 0.01 times 4 divided by pi times 0.25 square. So L is equal to 0.01 times 4 divided by pi divided by 0.25 square. This is 0.204 meter. And we know now that L is 0.204 meter. So we now know that the distance here is 0.102 because it's just the centroid of the displaced water. So our CG is simply 0.125 minus 0.102. And this is equal to 0.125 minus 0.102, 0.023 meter. And now I believe that we have everything. It's just to plug all the number and we get what is the GM. Okay, so IO is 1.917 times 10 to the power of minus 4 divided by our volume of displaced water is 0.01. This is minus 0.023. And therefore our GM is 1.917 times 10 to the power of minus 4 divided by 0.01 minus 0.023. And I will end up with minus 0.004. And that is your answer, everyone. So now we know that GM is minus 0.004. So the answer is, the object is unstable. And if you were to draw this again, okay, M would be under G. Okay, M would be somewhere here, meaning that the object is unstable. And that is basically how you determine whether or not the object is stable when it's floating. As usual, of course, there are more complex problems such as the actual ship, which has many components. For example, you have the offshore platforms, right? And there are many other floating objects where you need to calculate the GM so that you can be sure that the object will be always stable on top of the water. So now you are not only able to calculate what is the buoyant force, but now you also know whether the floating object is stable or not. And you do that by calculating GM using this equation. And as usual, my advice to you is to repeat this video again and again until you understand very well what is buoyancy and what is stability. That's all for this video. Study hard and I'll talk to you soon. Bye!